So, have you ever tried to learn a new skill, but you just find yourself falling back on a bad habit?
Oh, absolutely.
Yeah,
Because it's just easier. Right.
right, exactly. Like, we always think of habits as these purely psychological things. Like, if we just have enough willpower, we can break them.
Yeah. But biology plays a massive role there.
It really does. And it turns out mice do the exact same thing when scientists are, trying to teach them complex cognitive tasks. They find this physical loophole, like a lazy shortcut, and they just cling to it.
Right. And in behavioral science, we actually call that a choice
The
bias.
choice bias.
Yeah. It's basically when an animal has this overwhelming preference for one physical option.
Ah.
And they'll choose it regardless of the sensory info or, whatever the actual rules of the experiment are.
So if a mouse just likes the left side,
It will just keep picking the left side over and over, completely ignoring whatever perceptual puzzle the researcher's trying to get it to solve.
wow, which sounds like an absolute nightmare for a neuroscientist.
Oh, it really is the bane of our existence.
Well, that brings us to today's source material. We're doing a deep dive into this fascinating study from Scientific Reports today.
Yeah, it's a really clever paper.
It is, because they built this brand new, totally automated robotic system that's designed to train mice by dynamically correcting that exact choice bias in real time.
Which is a huge leap forward.
Right. So our mission for this deep dive is to explore how this automated system actually works, why teaching mice is so notoriously difficult in the first place, and how hacking a mouse's physical environment can drastically condense its learning curve.
And condensing that learning curve is just an absolute necessity for modern neuroscience.
Because the data has to be pristine, right?
Exactly. If an animal's behavior is all muddled up by its own stubborn physical habits, then any neural activity we record, like through imaging or whatever, is basically useless.
Because you don't know what you're looking at.
Right. We can't isolate the brain signals for memory or decision-making if the animal is just acting on a spatial reflex.
That makes total sense.
So fixing this roadblock required an engineering solution that could literally outpace the animal's own nervous system.
Okay, let's unpack this. Before we get into the cool robotic hardware, I think we need to establish the baseline here. What exactly are researchers asking these mice to do, and why do they fail at it so spectacularly?
Well, the standard behavioral setup they use is called a delayed match to sample task.
Okay.
It's this foundational tool for studying sensory processing and working memory. And, working memory is basically the brain's temporary workbench.
Like how it holds on to information just long enough to use it?
Exactly. So in this specific setup, we're looking at olfactory working memory. Smells.
Right.
The mouse is what we call head fixed. So its skull is secured painlessly in place. It can't run around.
Which sounds intense, but it's so they can use those high-resolution microscopes on the brain later, right?
Exactly.
Right.
So while it's head fixed, the mouse gets a puff of an odor, say ethyl acetate.
And then the odor stops.
Right. And then there's a delay period, usually like 1 to 4 seconds.
Which is a long time for a mouse, so it just has to sit there and retain that specific smell in its mind.
Yeah. And after the delay, it gets a second puff of an odor. Let's say 2-pentanone.
Okay, so the rules are pretty straightforward then. If the first odor and the second odor match, the mouse is supposed to lick a small stainless steel tube on its left side.
Right. The lick port.
Ah.
And doing that dispenses a tiny drop of water.
But if the two odors are different, so a non-match, it has to lick the port on its right side to get the water.
That's the whole game. It seems like a simple binary choice, but this is where that choice bias completely torpedoes the process.
Because of the lazy shortcut.
Exactly. Let's say you have a lefty mouse. It will just relentlessly lick the left port, completely ignoring the odors. It's not trying to learn the rule.
It's like taking a multiple choice test in a subject you don't understand and just bubbling in C for every single answer.
That is a perfect analogy.
Right.
Because you just happen to like the letter C.
Right, you're not trying to learn the material, you're just doing the bare minimum.
We call it a satisficing strategy. The mouse realizes, hey, if I just mash this less button indefinitely, I'll still get water about 50% of the time.
Oh, wow. So why waste the energy trying to memorize chemical compounds?
Exactly. And that strategy is deeply ingrained.
Mhm.
I mean, in the wild, relying on a default physical behavior is a massive evolutionary advantage.
Because it's fast.
Right. It lets the animal bypass the really energy-intensive prefrontal cortex and just rely on quick motor programs in the basal ganglia. Like if a mouse gets startled by a shadow, always darting to the left might literally save its life.
Right, doesn't have time to pause and compute the trajectory of a hawk.
Exactly. But in a lab where we're trying to map complex decision-making, That survival mechanism is just a wall of noise. The mouse isn't learning, it's just defaulting to a reflex.
So how did scientists fix this before they had all this automated robotic stuff? I mean, this can't be the first time someone realized mice are stubborn.
Oh, definitely not. But the historical fixes were, well, they were highly flawed.
How so?
The earliest approach was to just avoid the two-choice problem altogether. They used a go-no-go task.
Oh, so just one lick port.
Right, just one. And the rule was, if the odors match, lick the port. That's the go. If they don't match, suppress the urge to lick. That's the no-go.
I mean, that seems like a way easier task to teach. You completely eliminate the spatial bias because there is no left or right.
You do eliminate spatial bias, yeah. But you introduce a much worse variable, which is motivation asymmetry.
Motivation asymmetry.
Yeah, so these mice are on a really controlled water schedule. They are highly motivated to get that drop of water. So a thirsty mouse is just going to compulsively lick anything you put in front of its mouth.
Oh, so if it licks during a match trial, you don't actually know if it recognized the smell.
Exactly. We can't mathematically prove it learned the rule. It might just be experiencing this dopamine-driven compulsion to lick because it's thirsty.
And on the flip side, if it successfully doesn't lick during a no-go trial.
Did it remember the complex olfactory rule, or did it just get distracted for 3 seconds?
Wow, okay, so the behavioral data is just too murky. You can't cleanly separate memory from thirst.
Which is exactly why the field moved back to the two alternative choice task, the two lick ports.
Because offering water on both sides balances the motivation.
Right. The mouse is equally rewarded for a correct left lick or correct right lick, but as we established, that brings the spatial bias right back into play.
And it takes weeks or even a month to train them out of it. I was reading the older methodologies in the source text, and the manual fixes researchers used to rely on sound absurdly tedious. Like they would literally sit there and physically move the metal lick ports by hand. If the mouse favored the left port, the researcher would just manually slide it slightly further away.
And make it physically harder to reach, yeah.
But let me push back on this for a second. Why is moving it by hand such a bad thing? I mean, isn't that the simplest solution? Could a grad student not just nudge it back a millimeter?
Well, manual intervention actually breaks the temporal window of operant conditioning.
Okay, what does that mean in normal terms?
It means the timing of reinforcement in the brain operates on a scale of milliseconds,
Yeah.
and human hands are just way too slow.
Okay.
A researcher can't realistically evaluate a mouse's choice, calculate the degree of bias, and adjust a microscopic tube on a trial-by-trial basis. Not when the next trial starts 2 seconds later.
So the human lag time totally disrupts the feedback loop.
It disrupts it completely, and it introduces human bias. You're just guessing how far to move the port.
Right.
And worse, human intervention often creates new opposing biases.
Oh, like overcorrecting.
Exactly. Say you move the left port away to break a left side bias. The mouse gets frustrated, gives up on the left, and starts licking the right port. If you don't move that left port back to the center with millisecond precision, the mouse's brain immediately maps the right side as the new path of least resistance.
So you're just playing behavioral whack-a-mole.
Yes, you're constantly overcorrecting, which is why training dragged on for over a month.
Okay, so if human reaction time is the bottleneck, the only way out is automation. And here's where it gets really interesting. These researchers engineered a machine that reacts instantly to the mouse's biomechanics.
It's beautiful design.
Yeah. They took these two stainless steel lick ports, which, by the way, also act as capacitive touch sensors, so they know the exact microsecond the tongue touches them, and they attach them to linear actuators, basically precision motors controlled by an Arduino board.
And the speed of those actuators is the key. They move at 25 millimeters per second.
Which is fast.
Very fast.
Ah.
So when a trial starts, the ports slide right into place. If the mouse makes a correct choice based on the smell, it gets water, and the port stays there for an extra second so it can drink.
But if the mouse guesses wrong...
Both ports instantly retract out of reach, and it plays a 200 millisecond error sound.
But the retraction isn't just about denying the water, right? The core innovation is this two-layered algorithm they built to alter the physical geography of the mouse's environment.
Yes, the algorithm is constantly calculating. So the first layer is the long-term correction.
How does that work?
At the start of a session, it lets the mouse do 30 standard trials just to get a baseline. It evaluates the overall bias ratio, and based on that math, it sets a customized baseline position for the ports for that specific session.
Okay, and then there's the second layer, the short-term correction, which is trial by trial. This is so cool. So if the mouse licks the incorrect side, like it stubbornly defaults to the left when it shouldn't on the very next trial, that left port moves precisely 0.25 millimeters further away.
And the right port moves 0.25 millimeters closer.
It's like playing a racing video game with dynamic difficulty. If you keep crashing into the left wall, the game literally moves the left wall further away while giving you more right turns until you balance out.
That's a great way to think about it, because you have to consider what 0.25 millimeters means to a mouse.
It sounds like nothing to us.
Right, but for a head-fixed mouse using its tongue, an extra quarter of a millimeter requires a distinct increase in physical effort. The basal ganglia is constantly running an effort discounting calculation.
Like, is this reward worth the calories?
Exactly. By moving the preferred port 0.25 millimeters away, the system subtly increases the physical cost of the bad habit.
While decreasing the cost of the correct choice. What's fascinating here is how elegant the math is, because it actively rewards the return to cognitive effort.
Yes. If the mouse abandons the bias, actually pays attention to the smell, and makes a correct choice, the system immediately moves both lick ports one step back toward perfect symmetry.
So it only intervenes when necessary. It doesn't permanently handicap the space.
No, it doesn't. And alongside the physical distance, the algorithm also manipulates the probability of the trials.
Oh, right, the trial ratio.
Yeah, normally a mouse gets roughly 50% match trials and 50% non-match. But if the short-term algorithm detects that the mouse has made 3 consecutive wrong choices for the exact same side, it interprets that as a total abandonment of the rule.
It knows the mouse is just button mashing.
Exactly.
Yeah.
So the system increases the proportion of trials for the opposite side by...
Wow, so if it's blindly mashing the left button, suddenly 60%, then 70% of the trials are right-sided answers.
It mathematically stars the bias. It ensures the lazy choice almost never pays out.
So it combines physical distance with skewed probability to force the brain to engage the prefrontal cortex. That is wild.
It really forces them to learn the sensory rule.
But, okay, we have this beautifully engineered system, Arduino-powered, calculating effort, discounting on the fly. The real question is, does it actually work? Did it speed up the training?
The efficiency gains were staggering, honestly. They tested 11 mice, and like we said, hitting a reliable 80% accuracy threshold used to take weeks.
Sometimes over a month.
Right. With this robotic correction, all 11 mice hit that 80% mark in an average of just 7.64 days.
That is insane. They compressed a month of training into a single week.
And it held true even when they made the game harder. Remember the delay period between the odors?
Yeah, the part that strains their working memory.
The researchers increased that delay from 1 second up to 4 seconds.
Which is huge for a mouse.
It's highly demanding. But with the algorithm constantly balancing their biases, the mice adapted to the 4-second delay in just 1 to 4 sessions.
Unbelievable. And the study broke down exactly when these interventions worked best, right? Because manipulating the trial ratio did something different than manipulating the physical distance.
Yeah, that finding is so crucial. It exposes the timeline of how different brain regions acquire a skill. So, changing the trial ratio, skewing the probability that was highly effective during the early stages of training.
Early on when the mouse doesn't even know there's a rule.
Exactly. It's
Okay.
just probing the environment. So by overrepresenting the non-preferred side, the system forces the mouse to experience rewards on that side while the sensory cue is active.
Which builds the cognitive association in the prefrontal cortex. Like, oh, this sequence of smells means right side.
Exactly. The cognitive rule is established early.
But then later in training, changing the physical distance of the ports becomes more important.
Yes, the physical distance worked best in the middle phase of training, because by day 4 or 5, the cognitive understanding is there. But the dorsolateral striatum, the brain region for motor habits, it still has this lingering spatial reflex.
So the mouse knows it should go right, but its muscle memory is tugging it left.
Right. So physically moving that left port just out of reach severs that physical habit loop. It forces the motor system to align with the cognitive system.
Okay, I do have a serious methodological question here, though.
Sure.
Whenever you introduce complex hardware into an animal experiment, the risk of them finding unintended cues skyrockets. Animals are legendary for cheating on puzzles.
Oh, the clever Hans effect.
Yes. So if I'm a mouse and I have 2 mechanical linear actuators buzzing in front of my face, I'm not using my working memory to compare a smell from 4 seconds ago. I'm just listening to hear if the left motor vibrates at a slightly higher pitch than the right motor, and I'm licking based on sound.
And that is the exact vulnerability any peer reviewer would attack.
Right. So how did they prove they weren't just listening to the motors?
They ran an odor removal control test.
Yeah.
They kept the entire robotic system engaged. The delays, the moving actuators, the trial ratios, everything operated exactly the same.
But they changed the smell.
They removed them. During the cue presentation, instead of releasing ethyl acetate, the system puffed pure, odorless air.
Oh. So if the mice were cheating by listening to the motors, their accuracy shouldn't change because the motors sound exactly the same.
Exactly the hypothesis. And the result was immediate. The mice's accuracy plummeted straight down to 50%.
Which is just pure chance.
Pure statistical chance. They were entirely lost without the chemical cues. And the moment the researchers reintroduced the actual odors, accuracy spiked right back up to 80%.
So what does this all mean? It decisively proves the mice were genuinely relying on their working memory of the smell.
The robotics didn't teach them a new physical trick. It forced them to use their working memory. And, perhaps most crucially, it proved it doesn't create a permanent dependency.
Oh, they could turn the system off.
Yes. Once a mouse hit that 80% accuracy, they turned the correction algorithm completely off. The lick ports stayed perfectly symmetrical. Trial ratios went back to...
And the mice kept performing well.
They maintained their high performance, the bad habit was broken, and the cognitive skills stayed intact. No training wheels needed forever.
That is the ultimate goal. Alter the friction until the hard thing becomes the default, then take the training wheels away.
Exactly. And if we connect this to the bigger picture, it explains why condensing a month of training into a week is such a profound victory.
For the actual brain scanning part.
Right. When researchers want to understand learning at a cellular level, they track the exact same individual neurons in a live mouse's brain over time. They want to watch how specific dendrites change shape as the animal learned.
But trying to do that over 40 days must be incredibly unstable.
It borders on impossible. Brain tissue shifts, cellular expression changes, the microscope calibration drifts. The longer training takes, the harder it is to guarantee you're looking at the same synapse. But by shrinking that down to a single week, scientists maintain a perfectly stable optical window into the brain for the entire acquisition of the memory. We can cleanly isolate the exact neural circuits.
And because it's automated software, you don't just have to fix behavior. Could you run the algorithm in reverse?
That is the next frontier. Researchers can take a perfectly trained mouse and program the ports to induce a bias.
Oh, wow.
By slowly moving the right port away, even when the mouse is correct, they force it to develop a left side habit. And by doing this while tracking the brain, they can study the neural mechanisms of decision-making degradation.
So where exactly a bad habit physically forms in the brain circuitry?
Exactly. They have an automated tool to create, erase, and recreate habits while watching the neurons fire in real time.
That's incredible. So to summarize this whole journey, we went from mice trapped by their own evolutionary biology, useless for cognitive research, to a hyper-precise robotic system that recalculates their physical reality every millisecond.
Yeah, it dynamically alters the caloric cost of a mistake by fractions of a millimeter.
Forcing the animal out of its reflex and into conscious memory retrieval. It's brilliant.
It reveals something fundamental, I think. We view learning as this purely internal conscious effort. But this shows cognitive engagement is heavily dictated by physical convenience. The brain will only learn the complex rule if the physical environment mathematically prohibits the lazy alternative.
Right. Making the lazy choice just 0.25 millimeters harder is enough to make the brain realize, okay, fine, I'll learn the rule.
Exactly.
Which brings me to a final provocative thought I want to leave you with. This research highlights a stark reality about our own behavior. Our free will is really tightly constrained by physical convenience.
Oh, definitely.
I mean, the robotic lick ports didn't reason with the mouse. They literally moved the goalpost to make the lazy choice biologically expensive. Think about your own habits, the ones you rely on, just because they're frictionless. What if we could design our human environments with this same dynamic friction?
That's a fascinating idea.
Right. If your digital workspace automatically calculated your distraction bias and, say, physically lagged your phone screen by a few milliseconds every time you tried to open a social feed during work hours, would you suddenly find the cognitive energy to stay focused?
I bet you would.
It really suggests that the secret to learning faster isn't a stronger mind, but a physical environment that ruthlessly counterbalances our deepest instinct to take the easy way out. Well, that is all for today. Thanks for joining us on this deep dive. See you next time.